Hi everyone, so this is chapter 9 revision quiz, set 3. Well, even less responses, 17 responses. But yeah, we have one question to discuss, which is question 7. The rest has less than 10 people respond to it. Okay, so let's discuss question 7. Question 7 here mentions that you have a simple pendulum. Okay, and this simple pendulum is hanging from the roof of a stationary lift. Okay, when it's hanging from the roof of a stationary lift, this simple pendulum has period of capital T naught. Okay, when the lift is stationary, the period of the simple pendulum is T naught. Then when the lift is descending with uniform velocity descend, then the period is T1. Then when the lift accelerates uniformly downwards, then the period will be T2. Okay, a lot of information to unpack actually. So when it's hanging from a roof of a stationary lift, it has period T0. This is case number 1. When the lift is descending with uniform velocity, the period is T1. Descend with uniform velocity, it's case number 2. Then when the lift is accelerating uniformly downwards, that's case number 3. So for each of the cases, you have period T0, T1, and T2. So this question will ask you to compare between T0, T1, and T2. Okay, so let's try to think about this question. Okay, when it's hanging from a roof that is stationary, well, this case number 1 here is the case where we see in our chapter 9. Okay, when we talk about simple pendulum, we don't assume the ceiling is moving. You can think of it as being identical to a stationary lift. The ceiling is not moving up, the ceiling is not moving down. So in this case, this T0 here will be just equals to the SHM formula that we learned last time. It will be equals to T0 will just be T0 equals to 2 pi square root L over G. This is for the stationary case. Okay, now for case 2, the lift now descends with uniform velocity, and now the new period is T1. So T1, will it be appropriate for us to continue use this formula now that the ceiling is moving? Well, it depends on how it moves actually. So you see here, it says here the ceiling is going down. Descend means going down. The ceiling, or you can think of the lift, okay, but the main thing is the whole space is going down. It's descending with uniform velocity. If it's descending with uniform velocity, then you see that the acceleration will be what? The acceleration experienced by the lift itself, the elevator, the lift, the acceleration will be equal to 0 meter per second square for the lift. Well, if acceleration is equal to 0 meter per second for the lift, this case here is still exactly the same as this case here, because acceleration, okay, let's be more specific, in the y direction, is still equals to 0 meter per second square for the lift. Okay, because the lift is not moving, you can think of it as a net force equals to 0. So not moving is actually equivalent to moving down with uniform velocity. So for these two cases, since they are equivalent to each other, constant velocity, uniform velocity is equivalent to at rest. Okay, it's just that at rest the velocity is 0. It's still a uniform velocity, just that the velocity is 0. So in that case, there's not much difference between case 1 and case 2. It's still valid for us to use this formula here. Still valid to use this formula. Okay, so now we move on to the third case. The third case here mentioned that the leaf accelerates uniformly downwards. If it's accelerating uniformly downwards, it means by, for the third case here, acceleration in the y direction is no longer equals to 0 meter per second square for the leaf. Okay, so in this situation, if this acceleration is no longer equal to 0, well, this thing is probably not appropriate for us to use anymore. Well, we never teach this explicitly in your syllabus for simple harmonic motion, but if you see there's a g here, then you know that g is acceleration due to gravity. So if you see the whole leaf itself is going downwards with acceleration, you probably think that it will cause some effect to the g over here, because g is technically acceleration. Now you see there's changes in acceleration. Before that, the leaf is 0 acceleration in the y direction. Now it's no longer 0. So you can actually hypothesize that there might be changes to the bottom of the fraction here. So how does it change is actually slightly, should I say, it's a bit out of the syllabus. It's related to something called pseudo force actually. Or if you never heard of pseudo force, you probably heard of fictitious force. Okay. So this is a concept which might be difficult to understand. I learned about this in university as well, so I'm not sure whether this is in your syllabus or not. Fictitious force, right? It's not an actual force. It's a force that we create to make sense of the situation. Okay, I'll give you an example. If you are sitting in a car, wow, what kind of person is this? Okay, if you are sitting in the car and this is the chair of the car, and if this car is moving, then this person, if this car is accelerating to the front, okay, accelerating, so this is acceleration vector, is accelerating to the right, you actually, when you're sitting in a car and the car is speeding up, you can actually feel that you are being pressed into the chair, right? You will feel that you are being pressed into the chair. Okay, but actually there's no special force that is pushing you to the chair. It's actually the chair pushing towards you, making you feel like you are pushing towards the chair. It's complicated to imagine, but you can, to make sense of a situation, you can think of there's a force being created. Okay, this is called a fictitious force, a fake force. So you use this fake force to explain why you are being pushed into the chair. Okay, this is a fake force, and this fake force exists because the whole frame, okay, this is called frame, the whole situation here, wow, what's happening to my software? Because the whole frame here is actually moving with an acceleration. The frame, okay, we call it frame of reference actually. This is called frame of reference. Okay, because the frame that you are referring to, in that case our frame is the interior of the car. So it means that we don't know anything about the outside. Okay, our frame is the car, inside of the car itself. We don't have window, we cannot see outside. Okay, if this is the frame we are considering right now, and if the frame happens to be moving with an acceleration, let's say for this case it's accelerating forward, because you are in the frame itself, you cannot make sense why you feel this push towards the chair, because you are in the frame, you are not standing outside the frame. So you cannot see the fact that it's actually the chair pushing towards you that makes you sink into the chair. You are not standing from outside the car to see the situation. Okay, if you are standing outside the car, then you will see that it's actually the car moving, causing the chair to be moving, causing you, because of inertia, you have resistance to move. Therefore, this chair will actually push towards you, making you feel like you sink into the chair. This is what you see if you are standing outside the frame of reference. Okay, but because you are inside, you cannot explain this feeling that you have. Let's say you cannot see anything outside. You cannot see, you cannot feel anything outside, so you cannot make sense of this situation. So you are forced to create a fake force to explain the situation, or to explain the feeling where you sink into the chair. And this fake force that we create here is called the fictitious force. Okay, and the fictitious force is always opposite to the direction of acceleration. Of the reference frame, of the frame of reference. It's a very advanced concept. In fact, right, this thing, right, is used by Einstein. We call it the equivalence principle, to say that actually acceleration is equivalent to gravity. Then from that it derived the general relativity principle, the principle of general relativity. Okay, it starts from this equivalence principle thing. Well, it's advanced. If you don't understand, I can understand why you don't understand. Okay, but there's a lot of things which is related to fictitious force. For example, centrifugal force, the term that you might have heard of. You probably heard of it. People call it the opposite of centripetal force, but it's actually a fake force also. uh, Centrifugal force is a fake force. It's a fictitious force. And yeah, those are a few examples of fictitious force. So for this case, right, our acceleration, we are accelerating downwards actually. So if we are accelerating downwards, you can actually think of, you create a fictitious force towards the pendulum. Okay, now let me draw the situation. What's happening? Nothing works. Okay, so this is my lift and my pendulum is swinging like this. Okay, it's swinging back and forth. So now if my lift here is accelerating downwards, you can think of this pendulum bob here actually experiences a fake force, a fictitious force going upwards. Okay, just like here, because your frame is accelerating to the right, you have a fictitious force pointing to the left. Now because your lift is accelerating downwards, your pendulum bob, which is inside the frame, will experience a or we call it a fictitious force pointing upwards. And because you have a fictitious force pointing upwards and you have your weight pointing downwards, therefore these two actually are in opposite direction. Means by, for this situation, case number three here, your period will actually be less. Then your period will actually be affected because the G here, before that we only have weight and tension, but now you have this fictitious force which is opposing the weight. So actually the effective acceleration due to gravity will decrease. Okay, you can think of it as, never mind, let me describe that later. So you think that this acceleration due to gravity decreases. So if this term here decreases, oops, what's happening? Something wrong with my software. restart. Please wait for a while. Okay, now I'm back. So this thing over here is this thing decrease right now. Okay, decreases compare to case 1 and 2. Okay, so if this part decrease, this portion here decrease, what will happen is, because this is the denominator, decrease here will cause this thing to increase. Okay, increase in period actually means it will oscillate slower. Okay, oscillate slower, then it will take more time to finish one complete oscillation. Means by it oscillates slower. So in that case, T2 will be greater than T1, and T1 will be equals to T0. And your answer will therefore be this one over here. Okay, if you cannot understand all the fictitious fake things over here, one other way you can think about is let's say, right, probably you might remember, okay, usually we have a question that has a leaf and you are connected to a cable. Then you probably see before a question that asks you to snap the cable, then this thing falling, this leaf here is undergoing free fall, right? Let's imagine a situation. If this leaf is undergoing free fall, everything inside it will be undergoing free fall as well. In that case, you see that this pendulum bob here will fall with the same acceleration as the leaf out here. So you can think of this pendulum bob here actually floating in air, because it is falling together with the leaf. So it's not, this pendulum bob here is not sticking up, it's not going down. They are falling with the same acceleration, therefore this thing is actually floating in air. You can think of it as floating in the leaf. So if it's floating in the leaf, you can't oscillate like this if you are floating in the leaf. Then you can think that it actually takes infinite amount of time for it to oscillate back and forth, because it cannot travel downwards, because you are accelerating with the same acceleration downwards. So this ball here actually cannot go back to equilibrium position. If it cannot go back to equilibrium position, means by it cannot complete the oscillation actually. So you can think of it as taking an infinite amount of time to finish one complete oscillation, which is, I mean, parallel with what we are saying here. When we have acceleration downwards, you are increasing this period over here. It makes it oscillate slower. So if this acceleration here, if it's accelerating downwards with acceleration of g, it means by it's free falling. If the leaf is free falling, g, then a here will be equals to g if it's free falling actually. What happened? A will be equals to g if okay, again, A will be equals to G if the leaf is free falling. Okay, if the leaf is free falling, then acceleration will be equals to G. Then G minus G will become 0. So if divide by 0, then T here will become infinite. So it takes an infinite amount of time for it to complete one oscillation. If the leaf is free falling, like you cut the cable, then it free falls. Because this thing, the ball here is free falling together as well. So it can't move up, it can't move down, it can't move up, can't move down, you can't oscillate. That's why it takes an infinite amount of time to finish one complete oscillation. That's another way of thinking about it. So you are free to think whatever way you prefer. You can think of it in terms of fictitious forces, or you can put it to the extreme by thinking about a leaf which is free falling. Both of them, you will arrive at this answer at the end. Okay, so that's it for question 7. A very long explanation, sorry about that. Thank you very much.